Okay, so what we're going to do in this particular lesson is just talk about some of our basic rules of differentiation. So we have already looked at the definition of the derivative and how we can find that using our limit functions. And what we're going to look at now is just a few trick type quick tricks to be able to find the derivative functions in a faster method, especially when they're polynomials, right? So we're going to look at a couple of these. So the first one is the derivative of a constant function. So if you have a constant function where there is no second variable of x, it's just y equals a constant, such as what we have here is like y equals 8 or x equals 8, right? Or f of x is equal to 8 here, okay? If you were to take the derivative of that, it's always going to be 0, right? And that's exactly what this slide is saying, is that your df dx, your derivative of your constant function, will always be 0. And again, you can just kind of think about that pretty easily, because if what you have is if this is our xy axis, right, and we have a constant function, let's say f of x is equal to 3, right, we're just going to be graphing this horizontal line at 3, right? And if we're talking about derivative being the slope of a tangent line, if we draw tangent lines to a horizontal line, we're just drawing more horizontal lines, right? And as we're drawing horizontal lines, the slope of that is always going to be 0, okay? So any constant function, your derivative was always going to be 0. We can even look at that using our definition of a derivative to come up with a proof for that. So if we have that f of x is equal to c, where c is some arbitrary constant, and then what we have is using our definition of our limit as h approaches 0 of f of x plus h minus f of x all over h. Let's think about this. Our value of f of x is that constant c, and it doesn't matter what value we put in for x, even if we do f of x plus h, it's a constant function, it's always going to equal c. So if we use those in our definition of our derivative, our f of x plus h value is just a constant c. Our f of x value is also that constant c over h, and our c values there just are 0 over h, and it doesn't matter what h is going to equal, we're going to always have a value of 0. Right? There is no rise in our rise over run over slope, so we'll always have derivative of constant function being equal to 0. Right? So kind of going up from that, now if we look at rule number 2, which is the power rule, right, for positive integers of powers of x. So if you have some sort of polynomial where it's x to the power of a positive integer, right, the exponent is a positive integer, our rule for that is that when you take the derivative, so d dx, so taking the derivative of x to the power of n, right, where n is our exponent, what happens is the derivative is going to come from taking our exponent value of n, bringing it down and having it become the coefficient of our x term, and our exponent will get dropped by 1 and will become n minus 1, right? So a very small example here, if we have that f of x is equal to x to the power of 4, our derivative is going to be 4x cubed, right? Because this exponent of 4 is going to come down, become the coefficient of the term, right? And then our exponent value is going to get dropped by 1, so this was 4, 4 minus 1 is now 3, right? And that's going to be our derivative function. Okay. The proof of this involves having to use the binomial theorem, where you have to expand everything out depending on what the value of n is. But as we've kind of seen with our examples, what happens is that every term that doesn't have an h in it will always cancel each other out, and what you're left with is the second highest power, right? So if this was x to the power of 7, the highest power you're going to be left with is x to the power of 6, right, in your derivative function. Okay. So this also kind of applies in combining these two things, the constant multiple rule, where if you have a constant in front of a function, let's say 3x to the power of 4, right? So if you've got this variable to the power of an exponent, but then there's a constant out front, when we take the derivative of that, the constant still remains out front, and then you just take the derivative of that kind of inside function, right? So if our function u is equal to 3x to the power of 4, our derivative, right, of u, right, is going to equal that constant value, is going to stay the same. So in this case, it's 3, right? So if we make that, okay, our derivative of 3x to the power of 4, it's going to be 3 times the derivative of x to the power of 4, right? And we've just seen in the previous example that x to the power of 4 has a derivative of 4x cubed, right? Because we take our exponent of 4, bring it down for it to become the leading coefficient, and then we drop our exponent by 1, so it's 3. And then we can just simplify this by multiplying, right? So we can do 3 times 4 is 12, x cubed, and that's going to be our derivative, right? Now you can see that just as simply, just by saying, okay, if u is equal to 3x to the power of 4, you can also just look at it as, okay, again, we're going to take that exponent, we're going to bring it down, we're going to multiply it by that leading coefficient, right? So our derivative function, or du dx, is going to be 4 times 3, which is 12x to the power of 3, right? Because we're dropping that exponent by 1, okay? Now, with the next ones, with sum and difference rule, this is similar to like what we did with limits, where you can break your function up into 2 separate things. You can evaluate the limits and then add them up. Same thing with any sort of like type of polynomial functions. If they can be broken up into different terms, just find the derivative of each term and then just kind of combine them as much as you can. All right, so for instance, we have this function f of x, where f of x is 3x to the power of 4 minus 7x squared plus 9x. We've got 3 terms there. And we can use that power rule to evaluate each of them. So our derivative, f prime of x, right, so using this first one, we'll take that 4, multiply it by the leading coefficient of 3, and give us 12. X, drop the exponent by 1, and it's 3. Right, move on to the next term, right, take that 2, multiply it by the leading coefficient, so 2 times negative 7 is now negative 14, x to the power of 1, okay? Plus, then we can assume that this is an exponent of 1 here. 1 times 9 is 9, and this becomes x to the power of 0. But remember that anything to the power of 0 is just 1, right? So what we have here is that f prime of x is now equal to 12x cubed. Okay. Okay, where did that go? Okay, here we go. So we actually have here is now 12x cubed minus 14x, and this is now plus 9 times 1, or just simply put 12x cubed minus 14x plus 9, right? And there you go. Right? Now you don't need to be able to show this step, right? That doesn't need to be shown every time. You can just assume that when you take the derivative of a linear function like x, it's just going to end up being a constant like 9. Okay. So again, this type of power rule also applies for negative integers. So if the exponent that's on your value of x is also negative, the same rule applies. Where again, you're just taking that exponent value, you're bringing it out in front, right, multiplying it by the leading coefficient, and then dropping your exponent by 1. Right, so for instance, if our function is x to the power of negative 5, our derivative of that negative 5 is going to come down, get multiplied by the leading coefficient, which in this place is 1. So it's going to be negative 5x to the power of negative 6, right? Because negative 5 minus 1 is negative 6, and that's going to be our function, right? Now, again, using your exponent laws, you could simplify this a little bit, and then what you would have is negative 5 over x to the power of 6, okay? Recalling the fact that when we have exponents that are negative, we can take the reciprocal of the base so that the exponent can be positive. Okay, so you might see functions that look like that. Okay, so again, just another quick example here using these derivatives or these power rules, right? If we're trying to find dp dt, where p is equal to t cubed plus 6t squared minus 5/3 t plus 16, that derivative is going to come from doing it term at a time. So the derivative of t cubed will be 3t squared. The derivative of 6t squared will be 12t. The derivative of negative 5/3 t will just be negative 5/3, and the derivative of 16 is 0, so I don't need to write that, and then I'm done. Okay. The rule also applies, the same power rule also applies when the exponent is also a fraction, right? So just kind of quick example over here on the right. If we think about the basic function f of x is equal to the square root of x, how can we write this using an exponent power, right? So we can rewrite the square root of x using our exponent laws as x to the power of 1/2, right? And then we apply the same rule again, where now that we're taking the derivative, f prime of x, we're going to take our exponent and bring it down and multiply it by that leading coefficient. So it's 1/2 x now, and then 1/2 minus 1 would be -1/2 as my exponent. Okay? You can leave it like this, but you may also see solutions that start giving you a more compact solution, right? We're just using their exponent laws to simplify, which would essentially be 1/2 times x to the positive 1/2, which is the same as 1/2 root x, right? Again, that's all just using your exponent laws to be able to go through that, right? So we can then apply that to something maybe a little bit more complex, where you have y is equal to 3 times the 4th root of x. So once again, rewrite that using exponents, right? So what you would have here is 3, okay, it's jumped all the way back to the end again. Right? So you can rewrite this as 3 times x to the power of 1/4, because it's the 4th root in this case. Right? But then again, when we're trying to find the derivative, y prime, you're going to take that exponent, multiply it, right, by your leading coefficient. So that's 3 times 1/4, which is now 3/4, times x to the power of 1/4 minus 1, which is -3/4. Right? And while that's correct, we can often see this being simplified using those exponent laws as 3/4x to the power of 3/4. Right? And again, trying to write that using radicals. The denominator of our exponent tells us the type of root, so we have a 4th root there, and the numerator tells us what we're doing with it. So we have 3/4 times the 4th root of x cubed, and that would be our derivative function. Okay? So that's kind of just using those trick methods, right? And at this point, you should be able to do those, that worksheet that I sent you all away with. Just remember to try and rewrite your functions using rewrite them so that you can write them as a power of exponent, right? And then you can take the derivative using these methods.